Hi, everybody. Thanks for taking the time to come listen to me speak today. My name is Devin Baumer, and I'm working with Nick Bowis. And today I'm going to talk to you about my research, the geomorphic and hydrologic responses to beaver-related restoration at Bridge Creek, Oregon. So first, I'll give you a little background. Stream incision is a widespread, ubiquitous problem worldwide. Stream incision can happen naturally, but is exacerbated by land use practices such as agriculture, forestry, mining, and the removal of structure, specifically large woody debris and beaver. So channel incision results from rapid downcutting of the channel, which decreases the rapid downcutting of the channel, disconnecting the channel from the groundwater, which disconnects the groundwater from the riparian vegetation. And when the riparian vegetation is no longer supported by groundwater, it no longer supports the banks. So bank stability is further decreases further, and the channel continues to downcut until a base level control. These channels are highly simplified, high gradient, and generally poor habitat for aquatic species. In contrast, a healthy system is often multi-threaded, has many channels. It's connected to its floodplains, and the groundwater and stream channel are connected, which supports abundant riparian vegetation and creates plenty of complex habitat for aquatic species. So the cycling between the phases from which a channel becomes incised and recovered is described as recovering in phases. And this is depicted in the stream evolution model. So phase one is rapid incision, what we talked about before, where the channel downcuts rapidly, disconnects from the groundwater source. Second is widening. The channel end cuts and meanders throughout that inset floodplain, and it deposits sediment within the channel. As vegetation establishes within that channel, it reduces future erosion, and more sediment deposits on top of that, aggrading the system. And eventually, after cycles of widening and aggrading, the channel is reconnected with his historic floodplain, and groundwater is recharged and can support healthy riparian vegetation. And once the channel is connected to its floodplain, it can dissipate flow from high flow events, further reducing the chances for future incision. So this state dynamic equilibrium, you may have also heard referred to as stage 0. This process can happen naturally, but it takes centuries to millennia to occur. Whoops. Just making sure you're awake. In this paper here in 2014, Michael Pollock, Joseph Wheaton, and Nick Bowis expanded on that stream evolution model, suggesting that adding beaver would reduce the recovery time by increasing the aggradation in the channel, and furthermore reducing the aggradation and widening processes. For similar reasons, restoration practitioners use beaver dam analogs, which I'll call BDAs now. So BDAs are human-built structures that are aimed at mimicking the natural beaver dams and promoting the processes associated with them. This paper laid out the framework for how this experiment was aimed at working in Bridge Creek. So this ideology of mimicking beaver dams, which promote processes and create sustainable ecosystems, is the backbone of low-tech process-based restoration. So here is the manual for that. This practice has been, I'm really bad with this clicker. This type of restoration is widely applied. The problem is that few studies have quantified the responses to LT-PBR. The studies that have monitored usually only monitor for 1 to 2 years post-restoration, which isn't long enough for the expected recovery processes to occur. Other studies only focus on 1 to 2 structures. And although this gives us information about the local responses, it doesn't scale to the extent of what we're trying to recover. Overall, this type of restoration requires time. So we need long-term studies to quantify the long-term responses that we're expecting. So I have a unique opportunity to fill that gap by using 17 years of data collected at Bridge Creek, Oregon. Bridge Creek is a tributary to the John Day River in Central Oregon. Bridge Creek was established as an intensively monitored watershed in 2006 in response to an endangered steelhead salmon population. In 2009, over 4 kilometers were treated with BDAs aimed at promoting the processes associated with beaver, natural beaver, and also to support an existing beaver colonization effort. So beavers were trying to build their dams in these incised channels, and every time there was a high flow event, they would just get blown out. So these structures added a little structural support for the beaver so they could establish. This study has a before-after control impact design, so I can compare between treatment and control and over the long term. And I will be focusing on just these 2 sites right here for this presentation. The green star is the control reach and the pink star is the treatment reach. And here is a up close version of that. Those are my study sites. So previous studies have quantified the biologic responses to restoration at Bridge Creek. This graph is from this paper by Nick Bowis and others that looked at the responses to restoration. So as you can see in this graph, this is the number of beaver dams and BDAs. And after implementation, the amount of beaver dams and BDAs increased significantly. You can also see that there is a bit of a lag of an increase in the control reaches as well. So this suggests that the treatment reaches have become a source of beaver for the control reaches. And I will have to address that in my analysis. In addition, this paper also found that there is an increase in salmonid abundance, survival, and production. So we have these biologic responses, and I'm going to be quantifying the underlying habitat changes that occurred that elicited these responses. So I'm going to be doing that by looking at the geomorphic and hydrologic changes. So overall, if we go back to that Pollock paper, the aim is aggregation and widening and speeding those processes up. And those can be kind of broken down into segments of different expectations. So here are some examples of geomorphic. We're having more deposition as bars, the more channel complexity, and floodplain deposition. Hydrologically speaking, we're expecting a lot more water, right? And moving in different ways. So I'll be evaluating those using my 3 research questions. Did restoration implementation influence the extent and timing of a grading and widening of the channel? Did restoration influence the extent and type of inundation and channel complexity? And last, did groundwater table elevation respond to restoration implementation? So first, I will be looking at the geomorphology. In order to quantify the erosion and deposition within a reach at specific times, I'm going to be using digital elevation models derived from topographic surveying data from 2009 to 2016. And the way that you do that is you take the elevations from the older DEM and subtract them from the new DEM, and that gives you a DEM of difference. So in this figure, the blue is deposition, and notice that the deposition is occurring mostly in that main channel, which is what we were hoping to see. And the dark blue represents higher levels of deposition, and that's occurring behind that really large dam at the top there. Also, the red is erosion, and you can see that there's this new channel that formed from the old to the new, and there's erosion in that part of that surface, which is another thing we were expecting to see. Let's see. To do this analysis and calculate metrics, I'm going to be using the geomorphic change detection toolbar developed by Joe Wheaton and the Ecotopographic Analysis Laboratory. If you're interested in looking more into that, go to riverscapes.com. Yeah. Overall, I expect that the treatment reach is going to have higher levels of deposition and erosion than the control reach, and that the channel will erode through time. And that general aggradation is going to lead to more water on the surface, which will be my second objective, So next I'll be evaluating inundation, and I'm going to be using aerial imagery and drone flight imagery to manually map out the inundation extent and type. So these different colors in this inundation extent are different flow types. The purpley blue is ponded, orange is free flowing, and pink is overflow, which is just water flowing on a surface that was formerly dry, so new flow paths. Second, I will be mapping out dams and BDAs, so you can quantify the density of the dams in comparison to the water storage. And third, thalwags, so I can evaluate the sinuosity. So this increase in flow paths and water extent should provide more pathways for groundwater infiltration and water storage. So that's what I will be looking at next. In 2006, well fields were established adjacent to the control and treatment reaches at Bridge Creek and have been collecting hourly data since that time. So I'll use a time series analysis like this one, which is from an unpublished manuscript from that well data. All right, so I will calculate the average of well elevation from all of the wells within the well field, and then look at the departure from the long-term mean. So as you can see in this figure here, post-restoration, there's a larger difference between the control and treatment reach, indicating that there is indeed a response to the restoration. So I'm going to take all three of those objectives and link them together as they are simultaneously occurring through time. And by doing that, then I can evaluate trends in the data and then infer what those underlying mechanisms are that created those trends. And using aerial imagery, I can upscale that to network. So I'll be applying that over the network to see if the restoration worked at a larger scale which is what we expect from the process-based restoration and the extent that we restored the channel. So the main objectives of my research are going to be to quantify the geomorphic and hydrologic responses to low-tech process-based restoration at Bridge Creek. And this research will fill in the gap of monitoring studies and provide important feedback for those practitioners in the future. Overall, I'm looking at, we mimicked, the beavers helped promote some processes. Did we make a sustainable system, or did they make it? I guess it's them, not us. Anyway, I'd like to thank some people that have helped with this project. Nick Baus, my advisor, Joe Wheaton, Steve Bennett, Nick Weber, Carol Volp, Chris Jordan, Karen Bartlett, and our current funding provider, Think Wild. And I thought I should probably thank the Beaver too, because they did most of the work. Questions? Are you saying that based on the variation in flow?
Well, yeah, well, and erosion and deposition.
I don't think we've considered quantifying that part, but I think that would make a very big difference. So for example, I think it was in 2009, right after implementation of the BDAs, there was a high flow event and it just filled in everything. So that definitely makes a big impact on those different rates. I like that point. I want to like dig into that deeper of the DEMs. Okay, we'll have that too.
If you've got control sites over time, you can compare the difference between years across the control sites, right?
Mm-hmm.
So that the amount of variation that you see the control sites over time versus the amount of variation that's control versus
Yes.
you'll need to do both.
Mm-hmm. Yeah. Indeed. Other questions?
Can you describe a little bit more of the character of the Bridge Creek watershed? Is it public land, private land? Like, what does this watershed look like?
BLM and a lot of agriculture. Yeah, lots of hay and ranching. So
On the groundwater well slide that you showed, there were increases in both the control and the treatment reaches over time in groundwater.
mm-hmm.
Do you think that is related to the restoration itself and the kind of proliferation of beaver eating control reaches you're talking about, or climbing, or?
You know, I'm sure each of those could definitely be a part of it, but beaver did move into those control reaches. So I will definitely quantify this, but I think that is definitely associated with the increase in beaver and inundation overall.
On your hypotheses slide, you have those three graphs showing groundwater, wetted surface, and then sediment, I think is the top one, right?
Mm-hmm.
But sediment had an initial spike and then went up and down. So I was just curious why.
So the only, like in those figures, the data is accurate for 2005 and 2009 and like 2021, but I haven't done the in-between zones. But previous studies have found that sediment increases, deposition increases like right after beaver dams are built and they fill in, and then it kind of tapers off after that. And then also dams breach and blow out. So
You mentioned that in the fourth phase of the session that students actually goes back to the historic floodplain. Is that what's really happening, or are they just developing new floodplains? I'm just kind of surprised by that.
well, it's like, so those big terraces, those really high banks are the old floodplains. And then the idea is it's building up these mini floodplains inside the trench until it gets back to the level of its historic floodplain and reattaches. Yeah, well, that can actually happen naturally, that process of going back. And at Bridge Creek, it appears to have done so in certain places, but this is my qualitative analysis. Yeah. Anybody else?